Welcome to Brain Vision.
So first we start with a plot of the wave function and the probability density, and we note that the wave function and the probability density both approach zero as x approaches infinity or minus infinity, and both are also symmetric about the vertical axis, the y-axis. That'll be important in calculating integrals. So note also that the wave function is continuous. Even though the derivative is not. The first derivative may not be continuous, but the wave function is. So another property that we already noted is that psi, the wave function, goes to zero as x goes to positive or minus infinity. This means that the particle is in a bound state. So the particle is bound to x equals zero, which is the origin. Also, this means that we have a finite area under the curve of the wave function. So the particle can, or the wave function can be normalized. So we go ahead and normalize and we'll obtain a value for the normalization constant. So we start with our usual integral, but note, using the symmetry of the wave function, if we look at this curve, for example, we can say that the area on one side of the vertical axis, if we double that area on that one side, it is twice that area is equal to the area of under the entire curve for the entire wave function. So using that property, then this integral can be written as twice the integral under one side of the curve, and that's what we've done here, so that we can just integrate from 0 to infinity rather than integrating from minus infinity to positive infinity. And that makes the job of integration a lot easier. The whole process of integration simplifies. So carrying out the integral, we'll get the following. There should not be a square on the lowercase a there. So we'll just continue. And we get that, well, yeah, here we go. So you carry out the integral and you evaluate at the endpoint 0 and x approaches positive infinity, and you finally get that capital A squared over little a must equal 1, which means that capital A equals the square root of little a. So that's the normalization constant. Now we can calculate a probability over an interval. And this probability calculation is pretty much like the calculation for normalization. And in that sense, we go ahead and just calculate for one half of the area under the curve of the entire wave function, and then we multiply by 2. So we use that same trick, and we get the following result for the probability. This ends up being 1 minus e to the minus 1, which equals 0.632.